This conference will now be recorded.
And I have close enough, like more than 12 years, approximately of years of experience in DFT. So I have trained couple of batches here, almost like 10 to 12 batches over here, and many students, like more than 400 to 500 approximately in an average. So I explain the concepts in such a way. The teaching methodology which I follow is I will try to spend as much as of time available for a given topic, what we pick it up actually, and we will go for the practical session explanation also in parallel. So we pick a theoretical topic and we start some explanation, discuss something. So more often don't consider this like some training or like a classroom lecture or something like that. It should be more of interactive session, like a discussion it should be. That is what my intention. Then only people can understand and correlate the reality, how the conceptual topics what we have, like I follow in such a fundamental rule that people can understand the topics when we more discuss rather than lectures. Okay, so feel free yourself. Don't be feared to ask anything, to put on some question to me. You can interrupt me at any time. Some people may specifically restrict and tell, let me complete the entire session explanation and then you can come on to your questions. I am not such type of a person. You can stop me at any moment of time on the explanation topic. Imagine you are not able to understand, or you're not able to follow. So you have to come up with a valid reason and a valid point, what particular concept you're not able to understand, or what part of explanation you're not able to understand. I can repeat that for n number of times for you. Okay, so feel free yourself, comfortable, in a comfortable way, and you have to interact in a better way to understand the concepts. Okay, so that should be a small brief intro about myself and what I'm going to follow here. Type about yourself in the chat window, just your name and your previous decades of work.
Excuse me, sir.
Am I audible to you guys? I don't see any responses in the chat window.
Yes, sir. I don't know about others, but when we were speaking the last time, the voice is stucking, sir.
Okay, there can be some disconnect in the network.
Yeah.
It can be a
Can you
glitch.
please
So how
repeat
about
what you
now?
have said? It's okay. Can you please repeat what you have asked about this?
Yeah, I have just asked you to introduce yourself in the chat window by giving some basic details about yourself. Like you can write your name and what is your previous qualification of education, and currently what is your state of work. Are you looking for opportunities or you're working professional? Some basic details I would need to understand about yourself. Is it clear?
Yes, yes.
Okay, I see some couple of responses. I have gone through them. So many of you are actually looking for opportunities. That's what I understand. And some of you are also working in some MNC companies. Okay, fine. Good to know about yourself. So let me start the session for today. So I'll be giving some basic intro. Like most of you, it is the first class, right? So let me quickly grab some basics to understand what is DFT, and then we'll quickly jump into the one of the topic of DFT. Okay. I hope you're able to see my screen.
Yes, sir.
Okay. I will not spend too much of time here because just want to tell you what is meant by DFT and how does it look like. Okay. So what is the full form of DFT here? Design for testability. We can call it as design for testing, or we can call it as design for test, or design for testability. So the name itself here says there should be some design required. There should be some design required, which is specific for testing. So it is something like we are going to add, or we are going to have some designs that is very specific for the testing purpose. And what is this testing? So testing here is nothing but you are going to take a chip. You know what is going to be a chip or an IC by this time, right? An integrated circuit, or it's also called as a chip. So when you take a chip which is manufactured or which is fabricated, ideally in the processing of manufacturing, so or the process of fabrication, what we call. So once the fabrication has been done, the chip has to be tested. Someone has to certify it. Someone has to test it, or someone has to certify it that the chip is working properly, which means that there is no defect or there is no malware function which is there in the design or in the chip. So who is going to perform this test? Are we going to perform the test? No, we are not going to perform the test. There are there is a separate domain in the entire the VLSI industry what we have, or there is a separate team of members, a group of engineers who actually test the chip. So that the domain or the department or the section of the classification of this VLSI flow, if you go through, will have different domains actually. Like how you have different departments in universities and colleges, we have different domains in the VLSI. So there will be a separate domain called as testing domain. So the engineers who are working under the testing domain will actually test the chip. How do they test the chip? It is not something like very simple architecture, I would say, because a chip is a complicated, which is combined of multi-millions of gates, transistors, and some logic gates, right? So you can't simply tell that, okay, I'll give a value 1 here, I'll expect a value 1 here, or I'll expect a value 0. Is it that simple? No, because the functionality of the chip will be too complicated and complex. So you need some strategy, we need some method, and we need some concept that can tell that, yes, we are starting the testing of the chip. Who is going to tell that? Yes, the DFT engineers now comes into picture, which is nothing but we are going to have some designs. We are going to add some designs. We are going to have some new designs and tell that you enable my DFT, you enable my design so that it can start testing your chip. Okay, we can tell that we will add some designs. Our design will be responsible, or our design will be capable of testing the existing chip which has the regular functional design. So what is meant by a functional design? A design which is used for applications. So now what is application? Application is something the chip will be designed for a specific reason, a specification. What is meant by a specification? To what type of feature it has to work, right? To what type of feature it has to work, whether the chip has to work for a audio connectivity chip, or it should work for some Bluetooth activity drivers, or it should be working for some artificial intelligence, or for some large computing missions. What type of feature is what the device is being to be verified or to be integrated. So that is called the function of a chip. So we are not going to add the function of the chip. We are going to add the design that will actually test the actual functionality circuit, which is designed by some other designers. So now the design team is split into two. One, the regular functional design, like how the chip has to work or for what feature the chip has to work. And the second design team is the DFT design team, where we actually add some designs that are restricted to just test the chip. We are not going to add the designs for functionality of the chip. We are going to add the additional design into the IC, into the integrated circuit, just to validate or verify the existing circuit of the chip. Okay. Okay, I have one question here. Yeah, so the total duration of this course will be approximately 4 months, I would say. On an average, it can take from 3 to 4 months based on the interactions we are having. So if you are able to understand the topics in a quicker way, I would say 3 months should be good enough. If you are not able to understand the topics, you need some re-explanations and other things, it can go up to 4 months. Sometimes it can go to 5 months also, based on the people's interaction what I have. Okay. Okay. So I hope you understood what is meant by DFT and how it plays a different role in the entire chip compared to the regular circuit design. I have some slides here, like what is meant by DFT and all. So the functionality of the chip is 100% true, or it is 100% proper. The designer says that we don't have any issues, but still the chip is failing on the tester, on the silicon. So there is a testing engineering team, which I have mentioned here, and they started testing the chip and they have found some manufacturing defects. They have found some manufacturing defects. So who would be validating that? Who can identify that? The design team cannot identify, because it's multi-millions of gates and flops. It will be really tough for them to understand and to identify the issue. So we have some different types of manufacturing defects. So you may get a question, what is meant by a defect? When do we categorize, when do we categorize something called as a defect in the chip? So I have put some points here. There are something like point defects, and there are something like distributed defects, right? There are something like point defects and distributed defects. So what are these defects actually? If you see, there is something called metal scratches. What is metal scratches? Here metal speaks about a net connection in the design. We'll have wires and net connections, right? We'll have some wires and net connections. So those wires and nets connections, what if there is a scratch while manufacturing on the chip? It will automatically disturb the functionality of the circuit. In a way, it can be considered as a defect. And what is dark and missing wires? So wires is nothing but, like wires and nets, will have something called nodes. You might have heard about this during your digital circuit concepts. What is meant by a node? So wire connection is something like, I have a buffer and I have a wire connection to the next buffer. So this is a simple wire connection. What is a node? It also has one more fan out, which is going to some other AND gate. Imagine like that. And this particular point is called as node. The junction where between the multiple wire connections are divided into multiple wires or net connections. Ideally, we call this as fan outs. We call this as fan outs. Fan out means it is fanning out. This is one fan out, this is another fan out. So you have two fan out connections here. Instead of wire, we call that as fan out, right? So like that, we call them as valve nodes. So what if this is missing? What if the node is missing? Then automatically, how does it look like? You will have a buffer and it will have an output, and this is how it will be looking like. How does it look like? It looks like this, which means the connection has been broken here. There is nothing. So then also it can be called as a defect. And there can be something called poly cracks or poly bridges. What is meant by poly? A poly is it's a metal, or you can consider it's a material which is used to connect the MOSFET internal connections. If you take a MOSFET, you'll have something like this, right? Like you have drain, you have source, you have gate. So the connection between this gate and drain, or the connection between the drain and source, will be formed using a material called as poly inside the MOSFET. Okay, earlier I have spoken about the logic gates. The right hand side, I have spoken about the logic gates. Right, now I'm speaking about a MOSFET. So I hope you know what is meant by a MOSFET, right? Metal oxide semiconductor field effective transistor. So I'm now talking about a transistor level. So the connections between the gate and drain, or the gate and source, has some cracks or some bridges, then automatically it can be considered as a defects. So likewise, there are many other defects. I have pointed only few here called as point defects and distributed defects. So all these like ion implants, oxide thickness, metal width, metal thickness, all these things comes under like mask alignment, everything comes under when we do the manufacturing of a MOSFET or a transistor. So this is considered as a MOSFET. You will have something like drain and source terminal, and we will have something like oxide thickness layer here. Okay, and you'll have a gate terminal here. So there will be a channel formation here. Basically between these two there will be a channel formation. So it is something like fabrication steps of a MOSFET. If you understand what is meant by fabrication steps of MOSFET, all these things you'll be able to understand what is ion implants. So ideally there will be something like pumping of some ions into the via the gate terminal when you give the voltage. So this is all comes under the behavior of a MOSFET actually. And oxide thickness. The oxide thickness, there will be a metal oxide here, a layer which will be used as insulator for the MOSFET operation, and the metal thickness and width. So the connectivity also, we have earlier I have discussed about the metals, right? The logic connection, wire connection width, and wire connection thickness also matters. So if any of these things are violating, automatically my circuit behavior will change. My actual circuit behavior will change, which means my intentional output will not be appeared. So I could call that I'm getting a wrong output. I'm getting an errored output. I would say I'm getting a errored output. Why are you getting an errored output? Because of the defects what we have, which are in the design. Because of this defect, you're getting an error output. So instead of 0, I'm getting a 1. Instead of 1, I'm getting a 0. Something, an unintentional output is appearing because of the defects. So who can validate this? Who can identify this? Can the design team do this? Or there is another domain called as verification. Can the verification team do this? They can put their efforts. They can keep their 100% of efforts, but it is not that simple and easy to identify such issues. It is not possible to any other domains. It may be possible even if they keep 100% of efforts, but in a way there are chances that it may take too much of time for them to identify, or sometimes they may not be able to also identify. Because imagine there is a company A. A company is manufacturing a chip. A company is manufacturing a chip, and once it is manufactured, it has to go to some 3 products. Imagine like this, like it may go to a smartphone, and it may also go to some other application like some camera. Imagine, I'm just giving some vague examples to you to understand, make you understand. And imagine it's going to some other processor. So the chip which is manufactured should be used in 3 different applications which I have here: a mobile, camera, or a processor. But if this is a defective chip, then what happens? Will it work as intentional in the mobile feature? Will it work as intentional in the camera or processor feature? No, it cannot work. So there should be someone to certify that, because when you say like you want to buy a product, any product, anything, imagine you want to buy a smart television, you will automatically go and see the reviews, or you'll try to understand the manufacturing specifications, like what is the quality of the monitor, whether it is HD or full HD, right? High definition or full high definition, or is it something like a 4K vision, right? 4000 pixels, right? Or is it having some LED technology? Which type of LED technology it has, and what type of thing. So you also evaluate yourself when you want to buy a product, right? So there should be someone to certify so that they can release the product into the market, right? So that comes under who is going to certify that. The testing team will certify, yes, the manufacturing chip doesn't have any issues. But how do the testing team validate it? They don't know any knowledge about design, because design team is something different, testing team is something different. So without having any design knowledge, how do you test a chip? I'll give a small example. You are buying some product in the market, something like imagine that you have bought some smartphone or something like that. So if nobody has tested that product, without testing, can you blindly use that product? No. What happened? It may blow up, or it may not have the proper feature. The new smartphone itself, after buying within a day or 2 days, it may reduce its performance, where it's not charging, capacity is down, or it's not even switching on. So something happened. So it's called a defective product, right? So testing is very important and plays a key role in any product. It's not only this digital circuits and the digital environment, it can be non-digital environments. It can be like, imagine I would like to buy a sofa in my home, right? So you'd be testing it before. Okay, what is the sustainability, what is the durability, and how much weight it can weigh, right? What is the weight capacity of that sofa? You're going to test it. So without doing all these basic checks and testing, you won't buy a product. So likewise, in the chip industry also, if there is no one who has tested it, the customer or the market people will not keep interest to buy that particular product. And the biggest question which I have now, the testing team doesn't have any idea on the design. The testing team has no idea on the design. But how do they test it? See, if I know what type of sofa I'm buying, what type of material they have used, whether it is a cloth material or whether it is some other cuisine material, or what type of wood they have used, I can quickly check it. When you want to buy a furniture, this is how you check it. You know some specification, you can visualize it, you can see it. But how do I test a chip without knowing what is there? Can I open the chip and do something? No, I can't open the chip and test it. I have to keep the chip like this. I have some equipment called as tester. On the tester, I can place this chip, and hardly what I can do is like I can apply some inputs here and I can take some outputs here. That's it, nothing more than that. I can tell I'll apply zeros and ones here and let me get some values here, something like this. And I'll verify these values are proper. So without knowing what type of circuit you have internally, can you tell whether your output response is proper or not? No. So the testing team will never have an idea of the design, what the other team has built. Then it is too difficult. Without having any knowledge on the chip, how do I test it? Yes. So what we are telling is like we have an additional new design called as DFT. So you add this DFT. So the DFT engineer will tell that what inputs to be applied on the chip, what inputs to be applied on the chip, and we'll also tell what values will come out of the chip. We will tell that what inputs to be applied on the chip, and also we will tell what outputs to be observed on the chip. But how do I come to know that? We take some help of tools. We have some tools, what we call them as like automated tools. It's a software. There are some software tools that help us to do this operation, to add our design and to generate some values. What is that we are going to do? We are going to add the design and we are going to generate these values. So even I no need to understand even I may not understand the design explanations. Like I don't need to really understand the design conceptual. Even I am as new like a testing engineer. The testing engineer doesn't know anything about the chip. Even as a DFT engineer, I don't know anything about the chip. But yes, but still, you can add your additional design that can control the remaining actual circuit of the chip, and you can generate the values and tell, yes, these are the values you take on the tester, and when you apply these values, what is the expected response of the chip? The entire sequence can be provided by a DFT engineer. So we act as a medium platform between the actual designer to the actual testing team. So they have a new domain has been evolved into the VLSI industry, which is called as design for test, or also called as DFT team. Okay, I have a question. What are and all manufacturing defects? How do we answer? We have to tell point and distributed. See, there are multiple ways to tell what are the defects you find. If someone asks you what are the defects, if they are aware of what is meant by point defects and distributed defects, they can understand your answer. So in the other way, I would say like go for the actual explanations, like give some summarized points, Ramya. Like what is meant, you can tell, okay, if someone asks you what is a manufacturing defect, go ahead and straight away tell that there'll be some wire connections and metal, which are all called as metals in the physical design environment. So if there are some scratches on metals, or there are some cracks on the metals or poly layers, right? Or something went wrong during manufacturing of the chip, something like the ion implants are not proper, or the oxide thickness is not proper, it can automatically lead the misbehaving of the transistor or MOSFET. So you can answer that in the very simple point, rather than giving a overview. Because if I don't think so, like what is meant by point defects and distributed defects as of today, right? So if you go and tell this answer yesterday, I don't know whether you will be knowing to understand that point or not. If I come to you and tell that, okay, Ramya, do you know what is meant by point defects and distributed defects? You may not know that. So it is not like everyone will be knowing what is point and distributed defects. If they know, it's very well and good. What if the interviewer doesn't have the information like what is meant by point defects? They don't know. I'm not guaranteeing that everybody will be knowing it or everybody will not know that. So it's always better to communicate in a generic way rather than giving some very high technical terminology. Give in a generic way so that people will understand, because generic way is a regular English. Like if you understand what is metals are common, like everybody knows. People who are working in VLSI industry, they know what is meant by a metal. So they know what is meant by poly. So you can tell that what if there are scratches or some cracks on these metals and polys, it can lead them into a category called as defect. That should be your simple answer. Okay.
Okay, sir. Thank you.
So these are the different types of defects. There are few more number of defects also. I don't want to put all high technical terminology here. So I have just put some basic terminology to make you understand what is meant by a defect. Okay. You guys were able to follow the topic. See, I would pause my session every 20 minutes or 15 minutes or half an hour, 15 to 30 minutes in between. I would ask each and every one of you whether you're able to follow the topic or not. It's very important for me because I can't see anyone offline. So currently this session is online. I just will be relying on your responses to make understand that you are able to follow or not. So I need each one of you to type your responses in the chat window, whether you're able to follow or not. You don't need to, type lengthy statements. Just type yes or yes. That should be good enough, right? So my software will automatically tell me how many people have responded out of how many people have, or online, so that I can understand which of you have understood, which of you are not understand. As of now, I see 7 responses out of 24 people. So what about others? You guys were able to follow the topic? Does anyone has any questions? I still see some 15 responses out of 24. I don't know others were able to hear me or not. Okay, could I see 17 responses? What about others? Okay, good then. That's okay, Shravan. I think I didn't start much topics today. I'm just explained only one topic as of now, which is what is meant by defect and what is DFT. A small introduction. So we haven't started the actual course. Okay. Okay, let's go to the next slide quickly. So what is testing? I have already explained you this by some drawing diagrams. There will be a chip which will be in between. You apply some inputs and you observe some output. Nothing more than that. So I'll be sharing this material. Okay, like once I get all your Gmail IDs, your email IDs to me, I'll be getting it from the admin. I'll be creating a Google Classroom where I'll be putting all my notes also. Like say this is a demo session, so I'm not going switching between presentations and slides. But ideally what I do, I have a separate slide. If you see, I have some blank presentation. So here I'll be doing the drawings, writings, definitions, notes, whatever I'm trying to explain to you whenever the actual session starts. And I'll be sharing that material also into the Google Classroom. So I can show you something like previous batches which I have. So if I show you something like my scribble notes, so this is how it looks like. I'll be sharing, writing some diagrams. I'll be explaining something, do some drawings. As much as possible, I'll try to keep it in neat. If something I cannot, then it will be difficult for you to understand, but you can come back to me anytime. So like this, I'll be doing some drawings. I'll be giving some presentations. I'll be writing some paths. I'll be explaining there itself in my topics. This is how I actually follow. And these presentations will be shared to you when I write each and everything in the notes. Okay. Because I don't know whether you are able to write in a proper way in your notes what you have. That is very well and good if you take each and every micro details in from your end, but I will also giving my notes to you so that it will be helpful for you to later on to revise or to refer whenever you want. Okay. Okay, so coming back here, I have one more question. DFT means we are making the test easy or we are testing the design. We are making the test easy. That would be the appropriate answer out of the two statements what you have given. Okay, we are not testing the design because as I told, there'll be a separate team called as testing team who would actually do the testing of the design. But we give the database to them, we give the inputs to them. How do you need to test it? So they simply take our database, they test it, and they'll see. I'll come to that point. I mean, then I have in the presentations here in the next slides. How do we differ from testing team? Just hold on for like a minute. We'll be coming into that slide. So why do we need testing? It's very important point. So in order to guarantee that the product quality is very good, the cost is very important. So I have something called as rule of 10. So what is rule of 10? It means that as much as possible, the early the testing will save a lot of money to any company. How is it so? How do we say that the early the testing will help the company in order to save the money? So how do I mention like early in 3 terms? Whether you are doing the testing once the chip is been manufactured. So here I have 3 examples here. The first example here is like testing the chip or testing the chip on the board. You know what is meant by board? There will be something called PCB board. We call that as printed circuit board, right? Where all the chips will be integrated. Or whether you test it on the product, which is better. So why did I say early? Considering these 3 factors, I have mentioned that early. Imagine that I am testing, I skipped my chip testing, I skipped my PCB board testing, I directly tested the product and I found that the chip is defective. Then I have to scrap the entire product, which means there will be too much of cost bear on the product throwing into dustbin, right? So which is the best way? You directly test the chip. If it is passing the testing, then only you process this to the board. If the board testing is passing, then only you process it to the product. So in this specific category or in this specific abbreviation, I'm trying to talk the rule of 10, which says that the early the testing in these 3 mentioned options, the more saving to the company will be achieved. Okay. So this is the very old network chip. I just put into some explanation to make you understand how does a chip look like. So it has 12 million gates. 1 million is 10 lakhs, and here I have 120 lakh gates which I have, which is fit into 12 by 12 mm square. So this is 12 and this is 12 millimeters, like what you have the mm square size of the chip. It's very tiny chip, but it has too many number of gates and all, and it will have a clock frequency. So somewhere here there will be a clock to the circuit. So the clock frequency is something like 500 megahertz. So just to make you understand how does a network chip or a simple chip looks like, to give you some understanding, I have put this slide. So what do you think the major challenges we have here in the types of defects? Like what is the major challenges of the DFT? It's nothing but we have to identify the defects. There can be, so the defects are categorized into some faults. So in DFT terminology, right? DFT terminology, in the DFT terms or the terminology, I would say rather than calling the each and every defect, we categorize them into some faults. We categorize them into some faults. What is meant by faults? So fault is nothing but, I'll tell you here. Faults are nothing but classification of the defects we have in terms of fault. What is a fault? So I have a buffer and I have AND gate, and this AND gate Y is going to, sorry, this buffer Y is going to the AND gate A1. So this is my actual intention connection. But unfortunately, there is a defect on this net connection where the net connection has also as another connection which is ground to 0. There is a short connection. We call this as a short defect. What do we call this as? A short defect. So this short defect can be categorized into a fault called as this particular node or the net what we have, right? The particular net what we have, this particular net, I would say the net is always stuck to a value. The net is always stuck to a value called as 0. So I would say it is always stuck to a value 0. So even if I give 0 or 1 on the buffer input, for example, it is X, I mean the port name is X, and I'm giving a value 0 and 1, that value will not affect this A1 because the net is always stuck to a value called as ground or also called as 0. So this value which is stuck to 0, we call them as stuck at faults. We call them as stuck at faults. This is a physical defect. A physical defect here is a short connection between ground and to the net, which is unintentional. This is unintentional connection. This is not intended. This is unintended connection, and it is stuck to a value 0. So I call that as a stuck at 0 or stuck at fault. So a physical defect representation in a logical way, we call that as a fault. A physical representation of a defect in a logical way, you can call that as a fault. So there are many faults here which I have listed. Faults due to the nodes which are stuck to either 0 or 1. So it is not only 0. What if this z of the AND gate is stuck to value 1, which is VDD? Then it is called as stuck at 1 fault. So likewise, we have different types of faults also. Some of them are like delay faults. So delay always is not a manufacturing. Whatever you see here which is related to delay, these are not manufacturing defects. This is just performance of the chip. What is meant by a delay? How long it is taking for the signal to traverse from one point to other point? Like from here to here, how long it is going to take? That is called as a delay. If the delay is more, we can categorize that as a fault. We'll see the explanations in going forward classes. We'll understand how the delay is correlated to faults. How can we say it is a fault? So when we go for the topics in the next 2-3 weeks after, we have a topic called as ATPG, automatic test pattern generator. There we will discuss about what is meant by a delay fault. Okay, I hope you understood that. Okay, so there can be something called as bridging faults. What is bridging faults? The two net connections are short. See, earlier the short connection is between a net and a ground. Now this is one gate and this is another gate. Both the outputs are short. Then this is called as a bridging fault. This is also a defect because I'm not expecting this type of connection in between. So we can call that as a bridging fault. Okay, so there are other types of defects, like there is something called as leakage currents. So you know what is meant by leakage current? When the MOSFET is turned off,
Sir, you are not audible, sir. No, sir.
how about now? Am I audible to you?
Yeah, it's fine, sir. Now.
Okay, sir.
Yeah, I lost my laptop charging, so it is a small fluctuation. It got restored now. Okay, so I'm talking about the leakage faults. So what is meant by a leakage fault? So ideally for any MOSFET, when the MOSFET is inactive state, there will be small current that could leak from the MOSFET. So that's called as a secondary order effect of a MOSFET. If you go through the MOSFET secondary order effects, you will try to understand why does the MOSFET will leak a small amount of current when it is inactive. See, but ideally it's nothing but the operation of the MOSFET what we have. So when the MOSFET is in off condition, this is off condition, and this is on condition, this is saturation condition, something like that. So what the MOSFET is being operating for some time, and suddenly it is coming back to the off condition. So during that time, still there is a small leakage current into the design. So that can also lead into some defects. So we have something called as faults due to leakage current. There is another fault type of called as IDDQ, which is more relevant to the leakage current only. There is another type of fault called as IDDQ, which is quiescent current. IDD stands for drain current and Q stands for quiescent. Quiescent is nothing but again inactive. Inactive current, we call that as a separate fault. So likewise, the defects are categorized into different types of faults what we have here. Okay. So what is DFT? If someone asks a simple question, you can say to check manufacturing defects in the manufactured chip, some testing logic need to be inserted prior to the manufacturing. So during the design phase itself, so that once you add the design before manufacturing, so you can't add any designs after manufacturing. Once the product is made or once the chip is made, can you add some additional design into it? No. So to identify the manufacturing defects, we are adding some testing logic during the design phase itself. And this testing logic is dependent on the manufacturing defects that you want to detect. Which type of manufacturing defects you want to detect? Stuck-it, or this delay faults, or you want to detect the bridging faults, or you want to detect the IDDQ. So based on that, the logic insertion will also depend. Okay. I have one question from Karthik. Okay. What is, okay, stuck-it 0 and stuck-it 1. I'll redraw the circuit, Karthik. I have a buffer and I have an AND gate. This is also coming from another buffer. This is the circuit I gave for manufacturing. But after manufacturing, it happened like this. After manufacturing, it happened like this. So the design which I gave is the above one to the fabrication unit. But the design which I got is the second one. So I am not expecting any connection here. I'm drawing in small dots. I'll keep the pointer. I'm not expecting any connection here. But there happened a connection here during the manufacturing. This is unintentional connection. This is not my intention of the design. Right? So since the net is connected to a ground connection, we tell that this particular net is always stuck to 0, which means stuck at 0. If the same net, for example, the below net is connected to ground VDD connection, then we call this as stuck at 1. So both these short connections are unintentional, which means I did not give them during the design which I gave to the manufacturing. But somehow during manufacturing, the wrong implementation happened. I do not know what is the reason. There can be different scenarios. Why it happened, we do not know, but it has happened. So some implementation went wrong during manufacturing the chip. You understood what is meant by stuck at 0 and stuck at 1, Karthik? Okay, good. So let's go to the next slide. Fault models. I have already explained what is meant by stuck at 0, stuck at 1. And the delay faults I told I'll explain later on. And there can be something called leakage faults, which is called as IDDQ. As I just mentioned, this is IDD stands for drain current, Q stands for quiescent. What is quiescent? Quiescent means again inactive. So inactive drain current, when it is leaking, we call that as a IDDQ fault model. And I've also explained about bridging fault model. So there are n number of fault models. People are still introducing new fault models based on new technology nodes what we have. What is meant by a technology node? What is meant by a technology node? A technology node states the length of MOSFET you can consider, or the width of MOSFET. Precisely, I would say not length or width. You can consider length only, not the width. Width differs, length of MOSFET. The length of MOSFET is always calculated in terms of nano nms, right? We call that as nanometer technology. So if someone asks you which technology you are working, you should quickly tell them which nanometer technology you are. This is nanometer. So some would say like, I am working on a chip where the length of the MOSFET is 90 nm, which is 90 nanometer technology. 90 nanometer technology. Will we have 89? We can have 89, but what people has come up with, like the nanometer technology is something like they will going to decide the length of the MOSFET. So it is not a DFT team responsibility, but ideally they used to check from different aspects. How do they check from different aspects? Like they used to validate too many number of things, whether the MOSFET structure is proper, whether the MOSFET can bear the density, whether it can, the charging is proper or not in the MOSFET. Different parameters comes, and they will finally tell that, okay, this technology is stable. We see some stable results out of this nanometer technology. And in the market, different companies used to use that for their projects what they have. So if you ask me what used to be the earlier nanometer technology, people used to use 700 nanometer. Then they came to 350. Then we moved to 180. It's not exactly half. I'm telling all the stable nanometer technologies because they are handful. If you count, hardly like 10, 15 it will come. There are handful of nanometer technologies that gave us stable results during the fabrication of a MOSFET. So after 180 we have 130 or 140, but we consider 90 is the next one. After 90 we have the stable one is like 60. After we have a nanometer technology of 45. After that we have 28. After 28 we have 16. After 16 we have 10 and 12 are there. 12 is there, but not that much of stable. We used to have 10. So after 10 we have 7. After 7, the best results what we have is in 5 nanometer. And after 5, so currently the market is something like every company is striving like anything to work on 10, 7 or 5 in 2020. From 2020 onwards. From 2020 onwards, people are trying to go for lesser, lower technology node because the length of the MOSFET reduces, the size of the chip automatically reduces. Because I have 1 lakh transistors. If I reduce the 1 lakh transistors length, so automatically my chip size also will reduce. So there are some very rare companies where they are working on 1 nanometer also. Still some research is going on, something like that. So some companies are still telling that, okay, I don't want to go for very low technology now. I'm okay with my area of the chip now, all my features of the chip. My customer is okay with the chip size. I'll go with 45. Yes. So some projects work on 45 technology also. So it depends actually how the nanometer technology comes. So the lower the nanometer technology, new faults are coming into picture. Why is it so? Because the design size is gradually increasing like anything. So some new faults are coming into the picture, even for the DFT. Okay. So what are the different types of, we don't know it, what is after 1 nanometer. They are actually going for a different way. I'm talking about MOSFET. There are new technologies, like new inventions, like instead of MOSFET, they use a separate type of transistor called as FinFET. So it will have multiple fins, actually, like multiple terminals which come into picture, unlike MOSFETs. So people are trying to see, or people are also looking into, the MOSFET is built of silicon, a material from your periodic table called as silicon. So people are trying with some other materials also. So some experiments are going on still, right? So it depends. We do not know upcoming what it is. Like people can move to into different material, or they can move to a different structure called as FinFET, or they can reduce the MOSFET technology also. They can further reduce it in points or dots. But it is not completely possible to nail it down to zero, right? It is not completely possible to nail it down to zero. Somewhere at that point, at some point, everything will be saturated, which means you can't go beyond something, some limit. But still, people are trying their best with all the experts what they have. They're trying to see what further we can do upon this. So coming back here, we have different types of DFT logic insertions. Why do we need and what do we need? The first and foremost concept which I have is scan insertion. I have a concept called as scan insertion here. The scan insertion speaks about how to test the digital core logic, like the flip-flops and the gates. So all the flip-flops and the gates in the design will be tested using a concept called as scan insertion. Okay, I have something called as at speed testing logic insertion. It is also for the digital logic only, but this is something related to delays. Just now I have told no, something related to delays also. We have some manufacturing, not manufacturing defects, we have some fault categorizations. So the same core logic, it is not a separate insertion, it is a subset of this insertion, I would say. At speed test logic insertion, you can call that as a subset of scan insertion. So in the chip, it's not only a gate and a flip-flop. You can have a separate elements. There are different components actually in a chip. One of the other component what we have majorly see is the memories. So you know what is a memory? RAMs and ROMs. When you say memories, these are the two terminologies that populate into our mind in any one consideration. What is it? RAM and ROM. So if you want to test the RAMs and ROMs, you need a separate insertion. You can't simply use the scan insertion for the memories because it's a separate logic. So we have a concept called as MBIST. What is MBIST stands for? Memory. I'm writing here. If you want, you can take a note. Built-in self-test, which means it can test on its own. Okay, memories, built-in self-test. We'll explain that. I have separate planned theoretical topics. We have practical sessions. Everything is there. And we have another type of testing called as JTAG, logic insertion. This insertion can test the inputs, outputs of the chip. Because I have a chip, I'm testing everything internally. But what if there is a defect on my input, or what if there is a defect on the input outputs? Right, that can also lead some misfunctionality of the chip. So we have that called as a JTAG logic insertion. We have some dynamic BIST, we have some analog BIST. So these are specific related to IPs. What is meant by an IP? Intellectual property, which means it is designed by someone else, and more of we can have some analog logic. So for this also you'll have some built-in self-test, which is different from memory built-in self-test. Of course, memory is also a kind of like an analog circuit for me, but it is more often used in the chip compared to other analog circuits. What are the other analog circuits I have? Some amplifiers, some filters, some other different types of circuits we have in analog also. Can we test the analog? Not 100%, but we can try our best, because analog circuits are straight away MOSFET technology, right? It's a straight away MOSFET circuits. So DFT more often speaks about the digital environment. Yes, some part of analog and more part of digital. That is how the DFT is being evolved. Okay. So this is the same explanation, like fault in a simple inverter. Earlier I took a buffer and then and here. Now I'm taking a simple example of an inverter. Yeah, this is another good example, like how the faults can be looking like, or the defects can be looking like. Okay, how the faults will be looking like, or the defects will be looking like. So it is not like always a defect can be on the input. It can be occurred at any net connection. So in this case, it can occur on the output of an OR gate or an AND gate or any gate, any logical gate. It can occur on any other logical gate also. So it's independent. It is not like, okay, it will always target only inputs. We can't know, we never know that, right? So we have to consider the inputs and also the outputs of any logical gate, considering any single stucket fault. So which means that in this circuit, how many possible stucket faults will be there? Can anyone quickly tell me that? How many possible stucket faults are there in this circuit, circuit 1, and also in this circuit, circuit 2? So can anyone tell me that?
1, sir.
Just read the question properly. How many possible stucket faults can be there in the below circuit 1 and in the circuit 2? I see different answers, 3, 6, 1. Try to think.
6.
Take a minute.
Total faults, sir. You asking total faults or per node?
I just asked like how many possible stucket faults. You have to understand the question. The other part which I want to tell you, I would put many questions in terms of like interview point of view. Okay, so try to stick on to the question every time. Yes, when I say how many possible, I did not say partial or full. So which one is a better way for you to consider? When I say how many possible, when I say possible, you have to consider everything, right? Did you get my point? The person who has asked the question. Okay, let us see how many possible faults of stucket are there. So first, we'll see that how many stucket faults are available on a single net connection. So imagine that I have a single net connection, between A and Y. So how many possible stucket faults are there on a single net? I have 2. What are they? One is stucket 0. It can be possible. One is stucket 1, the other one which is possible. So if for one net connection, if I have 2 possible stucket faults, then what about the net connections here? How many net connections I have? I have net connection 1, 2, and 3, which means I will have 6 possible faults here. Okay, and on the second circuit also, I have 3 net connections. I will have 6 possible faults. See, this is very important question. People will ask. It can be a basic question, but people will stress on in some point of time in the interviews. Imagine that your interview have started. After 15 minutes, you are already in a deep discussion of some other topic like scan, M-based different topics. Suddenly they will pull to a basic question. Okay, how many faults you have? How many possible faults you have? It can be 6. You have to quickly not lose your basics. You have to quickly remember and tell, yes, I have 3 nets. Each net has a possibility of 2 possible faults. Either a stucket 0 come or a stucket 1 can come. because what is meant by manufacturing defect? We are assuming that there can be a defect. Nobody wants a defect before manufacturing itself. It is not possible, of course, but you can't tell that I want a defect. So I am coming with a question here. How many possible faults? Imagine that I have manufactured. In the worst case, can you tell me, after manufacturing this NAND gate of 2 inputs and 1 output, what is the worst case scenario that you see the defects? Which means I can tell, okay, I have to count myself. What is the worst case of possible defects occurring on this gate? Yes, each net can have a worst case of stuck at 0 and stuck at 1. Then I can say like, okay, three nets are there, 3 multiplied by 2, then I would say 6 possible defects can occur on this particular NAND gate. And it is same on the second circuit also, which is the OR gate. Did you guys understand? So it would be not 2 or 3 or 1 or 5. So people who have responded with 6 is the right answer. 6 in each of the circuits. Did you guys understand? I think one question, Veera, you asked how it is possible. Did you understand now or not? I don't see a response from you. You didn't understand? What is the point you have not understood? Can you highlight me that? I am waiting for your reply. Let me know what part you are not able to understand. I can take it and explain you again. Stuck at 0 or 1. One fault at a time. It may not be. See, when you say manufacturing defect, can you tell that only one fault can occur or one defect can occur, Sachin? No. What if it happens like this? What if it happens like this? It's a defect. It's a short connection. Can you tell that the short connection will be only one? I can't say that. It happens on how the manufacturing mistake is happening. So I can calculate both also. It is possible, right? We are just assuming. We are not perfectionally telling here that, okay, both will happen at a time or only one will happen at a time. We are assuming that every net can be possibly land up into 2 different types of defects. One is stuck to VDD or one is stuck to ground, or the same net connection is stuck to ground. So if I calculate logically, I would say that a net has a possibility that it can have 2 defects, or I could say 2 faults. So if one net has having a possible of 2 faults, then how many number of faults will be there on 3 nets? How did I get 3 nets? Because A is 1 net, B is 1 net, and Y is 1 net connection. So I have 3 net connections. So possible of 6 faults can occur. Is it clear to you, Veera? Did you understand how can we take 6 possible faults? So I am talking about circuit 1. It has 3 nets, possible of 6 faults. And the circuit 2 has OR gate. It also has 3 nets. It can also has a possible of 6 faults. Okay, that is a short presentation of my demo session which I had earlier. Let me continue to the actual slide and put on some other good question to each one of you. It's a common question. You can start, let me know, since we started this. Now, I would like you to do some exercise now itself, like how many possible faults are there in below circuits. I'll give some couple of circuits. You have to tell me how many possible faults are there. This is circuit number 1. Yes. So this is circuit number 1. I would say A, B, C, and D, and this is Y. So tell me how many number of faults, possible faults are there in this circuit. Quickly count and you tell me.
Sir, possible number of stuck faults or faults?
We are discussing about stucket faults. I didn't explain
Okay.
the other type of faults to you, right, as of now. So you can consider stucket faults only. Huh? If you are good enough to really calculate the other faults, I'll be really happy. You can explain me. So how many I have here? I see, why do I see different answers like 10, 20? How did you get 20? Can you guys tell me? The person who has answered 20, can you tell me that? How come it is 20? Pasyanti, can you tell me how it is 20? And Venkatesh, you have also answered it as 10. Pratap also 10. Can you guys tell me how it is 10 or 20? Okay, the appropriate answer is 16. Many of you have answered the right answer. It is 16 because I would say 2 here, 2 which is 4, and then 2 here, 6, 8, and then 2 more here, 10, 12, here 2 more, 14, and here 16. Very good. Now let's go to the next circuit and let me know how many we have. This will take time, I know, but you try to tell me how many faults are there here. I mean, if you want me to write some names, I can give A, B, C, and D, and I'll give some internal names also, this is E, this is F, this is G, and this is H, this is I, this is K, this is L, this is M, this is N, this is O, and this is Y. I see again why it is 24 or 26. You're not confident about your answer. How come it will be two different numbers? When you say possible faults, you have to consider each and everything. You tell how many number of faults we have? 30. Okay. 26, 24. So can you guys tell me how did you get 30? I would like to really understand. Well, let's calculate together. Let me know which all the faults you have considered first. As I gave some numbers also, I got 38, 32. Very diversified answers from each one of you. You're not able to calculate it properly, I would say, because you're not getting unified answers from everyone. Can anyone tell me how did you calculate the faults? Like you can write in the chat box, okay, A is equal to 2 or B is equal to 2, something like you write. I'll calculate here. I'll put some lines here and we can calculate together. You're getting 40 now. You're going to increase the count. Someone say like first earlier they did 20, 20, then it went to 26, 30, 24, 26, 30. Then we went to 30, 38, 30. Which one I have to take now?
Sir,
Yes.
sir,
Yes.
node A.
Okay. I'll take 2 points here.
Can you to draw, sir? You put the line.
Yes.
Okay.
I have already put it. Then.
Node A. E.
Okay.
B. F.
E also should consider or not?
Yeah. Yes, sir.
E, B, F. Okay.
F. G.
Okay. All the numbers,
G.
whatever I have written, you are telling it. Let me write it then. Okay.
I
Then.
don't know, sir. It's correct. I am guessing.
No problem.
D.
Give it back. There is nothing wrong.
D.
D. Okay.
D. H.
H. Okay.
H. I.
Okay. Yes.
And K and L. K.
A, L,
K.
E, L, I, E. Okay.
M. N.
Okay. Let us keep M. Let us keep N. And then 4 and then
Y.
Y. Let us count how many we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you made like 15 net connections here. Into 2, you might have given 30, right?
Yes, sir.
Is that what your answer is? People have counted 30,
Yes.
or you have something more?
So what about the D bar there?
That's what you have to tell me. How did the people
Yeah.
got 30? Have you
D
not
bar
considered
also
the
will
D bar?
when we calculate the D bar also there will be 32.
Yes. Okay. So let me put that also into consideration. As you said, then it will be 16 into 2. But nobody has told 32 to me. The chat window.
32.
Yeah, I did, sir.
Great. But still it is wrong. Let us see. So, okay.
Sir, we no need to take F and G, right, sir? Because it is a interconnection.
Yeah, I'll come to that point. See, why did I give this much of complex circuit? Before that, I need to explain you that a net connection from A to Y, you consider like 2 faults, right? But imagine the same net connection is going Y and is also going to X. Then you have to split this into 3 nets, not single net, because there is a node connection here. So as per physical design, whenever you have a node connection, which is nothing but that via connection, which I told in one of the point defects and all. So this will be a separate metal. Okay, this will be a separate metal, and this will be a separate metal. So which means that technically I have 2 faults here, I have 2 faults here, I have 2 faults here. Within this net connection itself, I have 6 faults. This is the proper. You understood why did I consider 6? Because when you have a node connection, the metal diversifies. The metal start and end point diversifies in the physical design, the actual physical implementation, which means technically A to this node is one net, node to that Y is another net, and node to X is another net, which means I'll have 6 faults instead of 2, right? So I have to consider them 6. So if I go back to my explanation here, there is a node connection here. So you have calculated on G, you have calculated on F, but you need to calculate on this output of inverter also, right? And here also, if you see there is a connection of net, then this will be, already you have taken these two, already we have taken these two, which means there is one more 2 faults here, and there is another 2 faults here. And similarly here also, on this first buffer output, there will be, already you have considered on the E, and already you have considered on the L, we have to consider the buffer output here. So which means that now 4 more got added, the black color lines which I have drawn, 4 more faults are also added now. So it will be 20 into 2. So whoever has mentioned the 40 is the right answer. Okay, did you understand the concept? How did we get the 40? Good that you guys have done the good effort of coming up to more than 30 plus, like 30, 32 or 36, whatever it is. So 40 is the right answer. You're able to understand how come I got 40 and what is the reason of getting 40? Why should I consider a node divided into 2 nets also be considered as separate number of faults? Is it clear or not? Can you guys type your responses in the chat window? I see 9 responses, 10, 11, 12 responses out of 23. What about others? You are able to understand how many number of possible faults are there now here? It would be 20 net connections you need to consider, which will be 20 into 2 is 40. I still see 15 people are clear with the topic. What about the remaining 7 people? Do you have any questions? Are you able to follow? I am talking here how many number of possible faults. We are not telling the manufacturing defect is there here. We are thinking like, okay, there can be a defect on this net. If that is the case, how many number of defects or faults can be there for the consideration of stuck-in fault category? A simple net connection tied to 0 or a connected to a VDD connection unintentionally. What about others? I don't see your responses. I see 15, 16 responses only. You guys don't want to, remaining people don't want to respond. Okay, fine. Okay, I'll save this presentation since I need to share it with you afterwards.
Excuse me, sir.
Yes.
I just have a doubt.
Your voice is too noisy and breaking. Can you check your mic?
Now is it? Yeah, 1 second. Now is it okay, sir?
Yes, it's a little better. Yeah, go ahead.
Yes. Sir, the output Y,
Okay.
will it have a fault, or the previous faults will be propagated there?
Okay, I'll ask you a better question. You have AND gate here.
Yes, sir.
Right? You have an AND gate here.
Okay.
Where is my marker here? Are you accounting the faults on the Y, K?
Yes, yes.
Why is it so?
So that is what I'm asking, sir. Is the fault occurring there, or it is a propagated fault? How should it be treated as?
This is not a propagation. I did not go to the propagation of faults. If you read my question, what is my question here?
No, I'm asking at the
The
final
question-
output, is the fault occurring, or because of the previous faults, that is a fault?
Okay, I understood your question, but I would like to get the answer from you itself. So I'm giving you some counter questions. My question here is, I am asking how many possible faults are there in the circuit, right?
16. Yes.
It's not 16, it is 40.
In
It's
the
in the previous
circuit, the
circuit.
previous.
That's okay.
Yeah.
In the
Okay.
previous
Okay.
circuit.
Yes, sir.
So here, did you account all the, so how do you calculate the possible faults? If single net is there, you are counting
Yes, sir.
2. If
Yes.
the
Yes.
node net is there, you are counting 6.
Yes, sir.
If this OR gate output is a net or not?
Yeah, it's a net, sir.
Can we have a defect here or not? Possibly.
Yeah. Yes, possibility is there, sir.
So the question here is how many possible faults? Are you going to account the Y here or not?
Yes, we will count it, sir.
So we got 16. Similar way, here also can this Y can have a possibility of a defect or not?
Yes. Yes. Yes, sir.
So I have counted 2 faults on this Y also.
Okay.
Okay.
Okay,
That
sir.
gives me total 20 nets into 2 is equal to 40 different faults.
Okay. Okay, sir.
Okay. Your point of fault propagation is far beyond of my conceptual explanations, which will come in the ATPG.
Okay. Okay, sir.
Okay. That will explain about what if I have a single fault or I have a fault here on the edge. How do I observe this fault? During that time, this fault will be propagated to the output side. That is a different concept.
Okay, sir. Okay, sir.
Now we did not land up into that concept. We are just keeping a basic circuit and we are trying to understand how many number of possible faults it can occur as per the circuit analysis. That's it.
Okay, sir. Thank you, sir. Thank
Okay.
you. Nice, sir. Thank you.
Okay. Good that you understood about this. So I have some questions for you, which you need to prepare by next class. I'll show you them, and if anything required, we will try to understand other topics. Can you guys quickly take down these questions? You can take a snapshot, you can take a screenshot. If you're willing, you can write in your notes. I don't have any objection. Okay. For the first week, after the first week, these are the questions I would like to give you. So I'll be putting it in every week so that you prepare yourself, and I will explain. Of course, I'll explain all these answers. You don't need to worry that you only have to break through these questions and all responses. I will also explain, but if you try to understand on yourself, you do some background work. I will also explain these topics that will help you to easily understand the concept. See, suddenly if I start talking about what is pad, you don't know what is pad. You will be completely blank. It may be a new topic for you. It can be a old known topic, or it can be a new topic for someone, right? So I don't want you to be going blank in the explanations. So try to do some background. It's kind of like an assignment. You have to understand the topic on your own. I know you may understand 100%. Sometimes you may not be able to understand 100%. What if you understood only 20%? You don't need to worry. By next week, we will start. I'll be starting the session with these questions only. I will explain 100%. That will help you to easily understand in less time. Okay. So I have some questions here, which I made, which are required for you to get to know by next week. Okay, so these are the questions. You can take these questions. See, a few things we may have already covered. Like, okay, why do we need DFT? The fourth question what we have is, why do we need DFT? Or the fifth one is like, what is manufacturing defect? Or the sixth one is, what is meant by fault? That's okay. If we have covered today, if you have understood, that's very well and good. You have to question yourself by looking into these points. Are you clear with these topics? So that the next upcoming topics will be very clear for you. Okay. See, as I mentioned to you in the starting of the session, my explanations I expect more often to be like a discussions rather than like a lectures. Okay. So you have to discuss with me. This is not this topic. Don't sit idle like how some people behave in colleges and universities. This is not a university lecture. I'm not going to give you any grades. This sessions will help you to understand, to train yourself to start or boost up your career in DFT. You're going to do a job, you're looking for an opportunity. So you have to behave and think in a real-time perspective. So that's where I'm trying to put up that environment here. So you have to come up with your questions, doubts, clarifications, and points, a new type of things, whatever it is possible from your point of view. That will help you a lot in many ways to prepare yourself, to prepare for interviews, and also how do you speak to experts, different things. Okay, so come up with these questions by next session. Try to fetch or try to get the answers yourself. See, if you are working professional, you're working from Monday to Friday, still it is okay. Spend at least 1 hour in the entire 1 week to Google these answers. You'll be able to crack them if you don't know them. Okay. So don't give some excuses like, okay, I have hectic work from Monday to Friday. I know that, even I am also a working professional. Then how do I provide the presentations to you? I can't sit only on Saturdays and Sundays to do that. I spend some time over the weekends, even if weekdays, even if I have some work. Hardly 30 minutes to 45 minutes or 1 hour is good enough. You need to have that dedication to get this. Okay. Okay, good then. So I'll stop the session for today. I will not pressurize too much. So we will meet on the next session. Yes, I'll not close the session. I'm just trying to put on some words. So the next session will be there in the next week, which is on next weekend, which is on Saturdays and Sundays only. So my sessions will be always on Saturdays and Sundays, even because I am also a working professional. I work as a DFT manager in one company. So I have my own projects, my own stuff during the weekdays. Okay. Okay, Sharon. And Purna, you have another question. How are the opportunities now in DFT? Very good question. The opportunities are going good. Yes, we had some downtime earlier, but now it is good. See, I started the session around 11, something like that, 10:50, 11. By 11:20, I got a message that, okay, we have DFT opportunities from some company. They're offering some internship or they're offering some opportunities. And this opportunity post is there in our VLSI group. It's not like somewhere in the other LinkedIn or some other post. We have new opportunities. The openings are there. Today also I see something like a company is require some DFT trained candidates at 11:20 in your previous batch. So opportunities are good. I would say like, okay, we have some sufficient opportunities. Okay. Clear to you? Purna Sai. Okay, you are from triple background or fresher for VLSI. That is okay. What is your question, Sachin? I understood your educational triple background, but what is the question? I didn't get you. Yes, you are fresher for VLSI. 2018 batch, yes. Any person who has not working in the DFT as of today will be considered as fresher for this DFT opportunities post this course. Imagine that there are multiple domains in VLSI, like physical design, verification, and all. You have 6 years of experience in physical design, and you want a future career. You give Can you be on mute if you are not talking? Okay. Tomorrow there is no session. As I just mentioned, my sessions will be on weekends. You can have sessions maybe from the junior tutors or some other session, like lectures which may be involved related to non-DFT technical stuff. I don't know that. You can check with the admin. But my sessions, you'll be finding me again on next weekend. Okay. Is it clear to you? Okay. Good then. How did you feel the class? Like, what will be the starting? Okay, you want to understand the starting fresher packages See, it depends on company to company, Karthik. I can't really tell you that, okay, this certain number, it may differ, right? So there are different types of companies in the industry, like service-based companies and product-based companies. So it is where something like you are trying to apply for the job and the company where is providing you the job. Some companies tell that, okay, I will give you, you know, hardly like 3.6 package per year, right? Or some people say we would give only 3. Some people would say like, okay, I will not get you paid for the first 3 months. We want to analyze your skills. Yes, we have a number of companies like that. Some other companies say, okay, we are product companies. We want to offer you like starting of 5 lakh of 5 lakh package or 6 lakh package. It depends actually. But I would say like the minimum would be like 2.4 to 3, not below that. If someone is offering below than that, I would not recommend at least, right? Or if some companies say like we want to take you as an internship, yes, then the package may be less. It may be like 1.8 or something. I don't know that exactly. So it all depends on which company you are choosing and which company is offering you. That is more important. Okay, it says getting updating now on it is. See, when you say like artificial intelligence, think in a positive way. Never think in a negative way. It will not allow you to grow yourself. That is a single fundamental rule, I would say. Okay, let the AI come. We are open to welcome it. But you also need to think in other ways. I'll give a best example. If the artificial intelligence is well developed in the market and everybody is using it, will it impact the DFT? Yes, it will impact the DFT. But is it going to impact your job? I would say no. The reason why it is, the more the AI develops, you think in the other way, the more number of projects will also will come, right? So you're thinking like, okay, in a project, the impact will be more. But I would say that you make it more number of, you will be open to more number of projects, which means still the human resources are required, right? So impact will be there, but how it will be there, in what way it will be there, according to me, I don't see a real impact. It can impact the project, but it may not impact the resources. I hope you understood my point, which I want to make here, right? So try to think in a positive way. Okay, did you get my point? Okay, other domains experience will be considered when we go as DFT freshers. See, it may go or it may consider or may not be considered. It depends on the interviewer or the company, because see, if you have some 5 years of experience in some other domain, I can't consider you as 5 years experience and pay you the pay scale here in DFT, because you don't know anything. You don't have experience of 5 years in DFT. Then how do I consider you 5 years of experience? So when you switch your career, 99% I would say like your, like expertise will be considered as fresher only if you are applying for DFT. Okay, is it clear to you, Karthik? Okay, but in DFT mostly are all automated. Yes, as of today it is automated. Last year also it is automated. Before year also it is automated. Next year also it will be automated. But in the past 3 years, did you see at least any impact in DFT? I didn't see. I see more opportunities, right? So don't depend on automation. You depend on the number of projects is what I would say. Automation is very good. I encourage automation a lot. Like I used to, Perl and Tickle scripting, correct? Using Perl, I myself wrote an automated tool. I'm good in Perl actually. So I have written an automated tool on myself. It may be a small version. It may not be a compact version. It is like a highly developed version, but still automation is good. It improvises your skills always, according to my learnings. Okay, you understood? Okay, good. Any other questions or queries you guys have? Do we have labs in afternoon? Today, I don't think so. But if you insist to have one, I can request the admin to conduct some basic lab session, asking if the mentor is available. I will be not taking the lab sessions, but I'll be explaining my lab, whatever the lab content is there, that will be explained by me in the theoretical first half of the session only. But what is lab session here? So here in this institute, there are two different things. One is lab explanation and one is lab session. Lab explanation will be taken by me in the regular classes. Lab session is something like you will be online and the junior tutor will be online. If you have any doubts, they will help you to understand that. If they were not able to still clarify your doubts, you can point me, you can reach out to me at any point in my number. I'll be creating a WhatsApp group hardly by next week where you can post all your questions there also. Okay, so don't get confused. Lab explanation is different here and lab session is different. Okay. Okay, so how did you feel the first session, people who are attending for the first time? I think many of you have already attended my demo session earlier. So I have taken good understanding from the other people. So people who are attending for the first time, do you see anything like you are able to match and correlate and you are able to understand the topics? You still feel any difficulty? You can let me know. You guys are on online. Okay, Pratap, thanks for that. You were able to understand that with the concepts. Thank you for all your comments. I would feel that okay, you are able to understand the concept. Good to hear that everyone is able to understand. Thank you for your feedback also. So we will be able to meet in the next session by next week on the Saturday. Next time I think I'll be try to be all on time. I'll not make you to wait you for at least 15 minutes like how I made you to do this today. I had some hurdles to join at 10:30. By next week we'll be on time. Like we'll start the session by 10:30 a.m. Okay. Offline sessions I am planning for this batch. We will see how it goes. So if you are interested to come to the institute, I am also interested to come because I started all these online sessions during the COVID session. Before that, almost like 4 batches I used to come to institute every week and I used to explain the topics. So I am planning for the offline sessions, but not every session, I would say like that. I am planning in such a way at least once in a month I would like to come offline for the entire weekend, which means on Saturdays and Sunday, at least 2 classes for 1 week, because hardly we'll get some 8 sessions. So let me start with 2 sessions per week offline, and if the response is good and if more people were able to attend, then I'll plan more number of offline sessions. But I have a plan to start offline from this batch. Okay. Okay, good then. So I'll close the session for today. We'll meet in the next class. So try to complete this assignment, what I projected on the screen. Thank you.